Now I will call the second speaker. Okay. The second speaker is from my own university, Shabbat Razavi. The title of the presentation is Assessment of Fatigue Crack Growth Behavior of Crack Specimens Repaired by Indentation. Thanks a lot.
Hello everyone, I'm Javad Razavi from Norwegian University of Science and Technology, and I would like to present a work that has been done for a couple of years in our group with the help of my supervisor, Professor Majid Ayatollahi in Iran University of Science and Technology. The topic is fatigue crack growth retardation using indentation method. As you may know, application of retardation methods in thin plates is something common in industries because you can extend the life of the component using different methods, and it's important mainly in aerospace industries and also marine industries. The presentation that I would like to present to you is about indentation method. So it is consistent of an overview of different retardation methods, the main objective of the work that we have done, and resultant discussion and conclusion. Cracks can form during the production and also under fatigue loading, and there are different ways to stop these cracks from growing, especially under cyclic loading. The main three different ways that you can solve this issue is to replace the crack component with a new one, reduction of loading level, or reduction of crack growth rate. Replacing the crack component is not always applicable because of the expenses and also sometimes due to the limited time that we have. Reduction of loading level, that is also not always possible because you have a defined load that is applied to the component, and it's not always possible to reduce this. But the third one, which is the crack growth retardation methods, it's mainly divided in three different categories. Applying compressive residual stresses that you can see: overloading, shot peening, laser shot peening, spot heating, and indentation. Or reduction of stress intensity factor using composite patches that are bonded on the crack component. Welding, which is removing the crack and filling the created notch with weldment. Crack filling using mostly resin and epoxy adhesives, or reduction of crack tip stress concentration using stop hole drilling, which is the method by drilling the crack tip. So the intensified stress at the crack tip will be diminished. But our work is related to indentation. As you can see in these pictures, this method has been widely used by indenting the crack tip, and by this work you can increase the fatigue crack growth life. It's mainly used for the repair procedure in airplanes, and there are some advantages. It's easy to apply. It's just an indenter that is applying a compressive load ahead of the crack tip. It's economical, it's time-saving, and you can use it for a wide variety of metallic materials. The key parameters which can influence the efficiency of this method are the diameter of the indenter, the indentation load, the location of the indentation, and also the thickness of the component, because you can mainly use this method for thin plates. We have considered some CT specimens made of aluminum plates with a thickness of 4 millimeters and three different configuration of indentation. As you can see in this picture, we tested crack tip indentation, crack flank indentation, which is double indentation on both sides of the crack, and treacle indentation at the crack tip and on both sides. Because the samples were thin, there was the chance to have buckling. So 2 plates, or it's better to say 4 plates, were used and screwed on both sides of the sample to prevent buckling during the testing, and the samples were tested under actual loading. Some finite element method models were used to capture the residual stress in front of the crack tip and along the crack tip, along the crack line. After conducting the finite element analysis using the plastic behavior that we obtained from tensile test on the aluminum, we were able to capture the residual stress in front of the crack tip. Here on the top curves, you can see the residual stress in front of the crack tip before loading, before actual loading of the sample, and after actual loading of the sample. So as you may see, the first one is showing the residual stress along the crack line. And the key parameter here was the indentation load. So there was just one indentation at the crack tip, and the indentation load was different. 1.75 and 2.5 kilonewton. It is obvious that by increasing the indentation load, the compressive residual stress at the crack tip will be larger. And that results in higher crack rate reduction, and consequently it will increase the fatigue life of the component. In this case, we were able to capture 143% of fatigue crack growth retardation, which is almost having a double life from a crack component. An important issue is that in this single indentation case, you can see that the compressive residual stress is followed by a tensile residual stress due to the equilibrium of the forces around the indented area. Here you can see the details of the fatigue test that were conducted. 3 tests were performed on each indentation loads. And here you can see the average value and the standard deviation. You can see that 33%, 67%, and 143% improvement in fatigue life were obtained for the crack tip indentation. The second case was double indentation on both sides of the crack tip. In this case, we used only 2.5 kilonewton indentation, but the key parameter was the horizontal distance of the indentation with respect to the crack tip. So 3 different horizontal locations as -2, 0, which is ahead of the crack, and h equal to 2 millimeter, which is in front of the crack tip, were considered. As you can see from the curves up here that are obtained from numerical analysis, you can see that the effective length, which is the length under compressive residual stress, is around 4 millimeter, which is 4 times higher than the single indentation. However, the value of residual stress is half of the value in single indentation. So there are some advantages and some disadvantages compared to the previous work that we did with single indentation. The value of residual stress is lower, which is not a good thing, but the length of the effective length in front of the crack is 4 times higher. And again, you can see that the best location, which is resulting the higher compressive residual stress, is h equal to 2 millimeter, which means that the indentation should be in front of the crack tip. And here you can see different fatigue crack growth rates for different cases. And just like what we get from the residual stress, the case with highest residual stress resulted in lowest fatigue crack growth rate and consequently higher fatigue crack growth life. in this case, 265% of fatigue crack growth retardation or improvement in the fatigue life was obtained, which is considerably higher than single indentation method, which was 143. The third case, triple indentation. In this case, we had one indentation at the crack tip and the other two which were in different horizontal distances of -2, 0, and 2. As you can see, this method has advantages and disadvantages of the other two methods. First, it has the advantage of the single indentation method, which is the high compressive residual stress, as you can see here, is almost the same as single indentation method, getting more. And it is almost more than it has almost more than 4 millimeter of effective length. Yes, there is this tensile part which is not favorable for us, but the compressive part is too much that we can just neglect that tensile part. In this case also, the best case for obtaining the maximum residual stress was H equal to 2 millimeter, which is indentation on both sides of the crack in front of the crack, and having the indentation at the crack tip. So for single indentation, we had 143%. Double indentation in the best case was 265, and for triple indentation, we had 435% of fatigue crack growth improvement, which is 4 times higher fatigue life by this method. Afterward, the failed samples were analyzed using SEM. As you can see here, the micrograph of plain specimen without indentation, and also the other samples are shown. As you can see, stable crack growth with this situation are obvious for the indented samples, and this stable crack growth was longer for the samples with double indentation and triple indentation compared to single indentation. Besides that, when we went closer, we could see that the distance between these extraction lines were smaller, showing that the fatigue life is higher in these cases, which is the same thing that I show you in the tables. Conclusions. For the single indentation case, we saw that the compressive residual stress exists in front of the crack, followed by the tensile residual stress, and higher indentation load results in higher compressive load, which results in higher fatigue life, which is obvious, and in accordance to the work done with Goto in 1996. And for double indentation method, we saw that there is no tensile residual stress in front of the crack tip. It's all compressive, but the value is lower, but the effective length is higher. And that caused, at the end, to have higher fatigue crack growth retardation compared to single indentation. And at the end, triple indentation had high compressive residual stress and longer effective length in front of the crack, and effective crack extension of 435% was obtained by this method, which is the method that we suggest for application. It should be reminded that all samples were tested under mode 1, and all samples were made of thickness 4. So it is possible to change the thickness and see the effect of the thickness. It is possible to run experiments with mixed mode loading, and it is possible to also change the vertical distance of indentation in accordance to the crack tip. For more information, because the preliminary results of this research was published recently in the Journal of Fatigue and Fracture of Engineering Material and Structure, so you can refer to that paper to see more details about the experiments and numerical results. Thank you very much.